Today, we're going to walk through an approximation method we developed. It's designed to describe the really complex CH stretching region you see in the vibrational spectra of large molecules, and we'll be focusing specifically on how it applies to polyaromatic hydrocarbons.
All right, let's jump right in. We've broken this down into 6 parts. First, we'll set the stage with what we call the CH stretch challenge. Then, we'll introduce our divide and conquer method and how we built it. After that, we'll look at 2 case studies, naphthalene and anthracene, before wrapping up with a look at just how efficient and accurate this new method is.
So let's get started with Section 1, the Chat Stretch Challenge. We like to think of it as a kind of computational traffic jam, and you'll see exactly why in just a moment. This really gets to the heart of the problem we wanted to solve. Why is this specific slice of the spectrum, from about 2800 to 3100 inverse centimeters, just so incredibly difficult to analyze with any real accuracy? Well, it turns out there are a few big reasons. First, you've got these strong Fermi resonances, basically interactions between energy levels that just scramble the intensities of the fundamental vibrations. Then, as the molecule gets bigger, the sheer number of possible states, or the density of states, just skyrockets. This leads to all sorts of mixing, and the bottom line is, trying to do a full, accurate calculation for these large molecules becomes computationally intractable. It's just not feasible. So how do you get around that? That brings us to Section 2, and the solution we came up with, a divide and conquer method that acts as a new approximation for the very accurate vibrational coupled cluster method. The whole foundation of our work is the Vibrational Coupled Cluster Method, or VCCM. Now, this is a fantastic quantum mechanical tool. It's incredibly accurate for describing the tricky anharmonicities in vibrational transitions, because it treats the interactions between states exactly, at least within its own limits. But all that accuracy comes with a hefty price tag. The VCCM has a major computational bottleneck. The size of the main matrix you have to work with, the effective Hamiltonian, it grows exponentially as you add more vibrational modes. For a big molecule, building and solving this huge matrix just becomes impossible. So here's the strategy we developed to get around that. We used a divide and conquer approach. We split all the vibrational modes into 2 groups. On the left, you see our high-priority target set. This includes the CH stretching modes themselves, plus any other modes that are strongly coupled to them or are in strong Fermi resonance. Everything else, literally every other vibrational mode, gets put into the bath set on the right. That leads us right into the how. In this next section, we'll break down the specific methodology we set up to systematically build this really crucial target set. It was a systematic 4-step process. First, we ran what's called an effective harmonic oscillator calculation for all the modes, just to get a good starting point. Then we applied 2 thresholds that we can define. A C threshold helped us find modes with strong cubic force constant couplings, and an F threshold let us pinpoint modes in strong Fermi resonance. And finally, and this is the real key to the whole thing, we constructed and solved the VCSEM equations for only that much, much smaller target set. So that's the theory, but how well does it actually work in practice? To find out, we first applied the method to naphthalene, which is the smallest of the polycyclic aromatic hydrocarbons. On this slide, you can see how our calculations stack up against the real-world experimental data, which is that green line at the top. The purple line at the bottom shows our calculation using a C threshold of 200 and an F threshold of 250. And as you can see, our calculated spectrum does a really great job of reproducing the key experimental peaks. It actually turned out to be a slightly better match than the other sets we tested. And if we zoom in on the details, you can see just how well it performed. Our chosen target set was able to resolve those 3 distinct bands labeled O, N, and M. For the peak labeled R, we even got the intensity ratio right relative to the O band, which is a lot closer to the experimental spectrum. And this is really important. The P band, which was completely missing in our less refined calculations, now shows up. So we're not just getting the positions right, we're capturing the intensity distribution too. So for our next test, we decided to up the ante. In Section 5, we applied the method to a larger and way more computationally demanding molecule, anthracene. And this is where the robustness of the method really shined. I mean, despite all the extra complexity and the much higher density of states you get with anthracene, our calculated spectra still show really strong agreement with the experimental intensity pattern. And that was true across all 3 of the different target sets we tested, which you can see compared here. What's so crucial here is that even with that much more crowded spectrum, the 250C200F target set was more than enough to get excellent results. We correctly identified that the most intense experimental peak, labeled T, was actually a mix of two intense calculated transitions. We assigned our peak as well, and all told, we were able to identify 12 distinct transitions from the experimental spectrum with this pretty small target set. Okay, that brings us to our final section. Let's pull it all together and summarize the key benefits of this new approximation in terms of its efficiency and its accuracy. This number right here really says it all. In some benchmark tests we ran on the parroting molecule, we found that our method reduced the computational time by over 95% compared to a full VCCM calculation. And what's truly remarkable is that we got this massive speed up while still maintaining a very high degree of accuracy in the results. So what are the main takeaways from all this? First, this approximation makes VCCM calculations way, way cheaper computationally. Second, as you saw in the case studies, it still accurately reproduces the really complex features of that CH stretch region. Critically, it also holds on to the multi-quantum nature of the transitions, which you absolutely need for a correct physical picture. And finally, this approach isn't just for CH stretching. It could easily be applied to other high-energy regions like NH or OH stretching. So in the end, this work makes accurate vibrational analysis of large molecules something that's actually feasible, computationally speaking, without having to give up the critical physical details. This really opens the door for a lot of new investigations, and it leaves us with a pretty exciting question for future work. What larger, more complex molecular systems, things that were previously just out of our reach, can we now accurately explore with this efficient new method?